All right. So hello, welcome back. In previous videos, we started looking at curvilinear motion and we defined position as a general vector pointing from a reference location to the location of the particle. And from there, we defined velocity to be derivative of position and acceleration to be derivative of velocity or second derivative of position. So we defined these and we saw how they kind of look like graphically, but actually the way we are seeing this as I have drawn here is not useful on its own, because to work with any of these you need to know what is R. How do you write it with numbers? Yes, you can create a graphic vector, but you cannot do proper calculation on it unless you associate it with some kind of number, numeric values, and some equations. So the main issue at hand here is how do you write a vector in a mathematically usable form. Note that a vector is a quantity that has magnitude and direction. It exists in for instance, a three-dimensional space. The question is, how do you describe that? We will see different ways you can describe the same vector in different coordinate frames. The easiest one that we'll start working with is rectangular frame, or the Cartesian frame that you're probably most familiar with. That is the space or the vector space defined by three perpendicular axes, axis x, y, and j. Why did I say j? Z. X, y, z, yes. It's a right-hand frame, the good old-fashioned frame that we're all familiar with. Now in this frame, if you have an arbitrary path, a location of a particle, note that it is still the same thing, same vector r that I had up there, but now I have access to some known directions that I can start associating numbers with this vector. So in Cartesian frame, I have these unit vectors I, j, and k, each one along the directions of axis x, y, and z. And if I have this, let me do green. I can project my vector r onto these axes and calculate the component of the r vector along these. So I have ry, rx, and rz. Now things start to take form. I can write the vector r using its component, essentially rx plus ry plus rj. Why do I say j? Rz. Completely arbitrary. Why do I say j? So it's a summation of these three green vectors. Or I can write them in a scalar form. Rx is a magnitude of Rx along I plus Ry along J plus Rz along K. So now I can actually go have a tape measure, measure the components, the distances of the projections from the origin along any of these axes, and write vector r using useful numbers. So that is our our position vector. Now that I have equations and numbers, my life is a lot easier. Let me clean up here. I can write velocity, that is d over dt of r. And taking derivative of this kind of equation, is what I have is essentially a summation of three terms. Derivative of summation is the summation of derivatives. So I have d over dt of rxi plus d over dt of ryj plus d over dt of rzk. And because these unit vectors I, j, and k are constant, they are vectors that don't change. They are sitting happily in a space. They are there. The only thing that changes, possibly changes with time, are these components, rx, ry, rz. So if I take the derivative, that becomes drx over dt in I direction plus dry dt in j direction, drz dt in k direction. And let's see what each of these are. If you look at the projection of this along the projection of the vector r along any of these axes, I have three dots that go back and forth along these axes. So each of these dots has essentially a rectilinear motion along the known directions. Our x, our y, and our z are the positions along that. And time derivative of those positions gives me velocities in those directions. Vy j plus vz k. So in other words, my vector of velocity is created by considering the components of the velocity along each of those directions. So there is this nice separation between different axes of motion. All I need to do is calculate individual components of the velocity, and my total velocity vector is the summation of all these three components. And following exactly the same footsteps, I can also calculate acceleration vector. If you do exactly the same thing, you will arrive at axi plus ayj plus azk. That is the total acceleration vector is created by considering the individual components of acceleration along any of these directions. Let me actually add another thing here. Velocity, you can also write it as rx dot I plus ry dot j plus r dot zk. So taking time derivative of individual components. Similarly for acceleration, you have r double dot x I plus r double dot y j plus r double dot zk. If you know any of these variables, the accelerations, positions, or velocities for any of these components, you can take either derivative to go back or maybe go forward, I don't know which direction, or integral to find other ones. So with rectangular frame, it becomes really easy to work and go from position to velocity to acceleration, or the other way around using integrals. And that really helps us with calculation, this nice separation. This rectangular frame is not the only one. In the next classes, in the next weeks, we look at a couple of other frames that are useful for other scenarios. For instance, if you have perfect knowledge about the path or some rotational aspects of the motion, you will see different frames can be more handy. But for now, I leave you with this rectangular or Cartesian frame, and we'll see example of it in class. So I'll see you there.